Welcome to Engineering Studio with Dr. Mohammed Tahir. In the previous video, we studied about the failure modes of compression members, local instability and global instability. And we have seen that the overall buckling or global instability of a compression member is governed by the slenderness ratio of the member. So in this video, we are going to study about the slenderness ratio, how it is calculated, on what factors the slenderness ratio depends. So first of all, slenderness ratio. Slenderness ratio is the ratio of effective length of a member to the radius of gyration of the section. The slenderness ratio depends on the three parameters: effective length factor, unbraced length, and radius of gyration. So these are the three factors on which the slenderness ratio depends. Effective length factor K, which depends on the end condition and end condition of the column. So this K factor, this depends upon the end condition of the column. The second one is unbraced length of the column in the direction or in strong direction or in weak direction, whichever gives the more answer for KL over R. And the third parameter is radius of gyration, which may be Rx, Ry, strong and weak direction for uniaxially and biaxially symmetrical cross sections, and least radius of gyration Rz for unsymmetrical cross section. So this L and radius of gyration, we need to consider these factors K, Lu and R, the corresponding value for which we are going to consider. And if we want to get the maximum slenderness ratio, then we need to consider the minimum radius of gyration and maximum effective length or unbraced length to get the maximum value of slenderness ratio. So one by one we will discuss all these parameters. What are these and how we can calculate these parameters? So first of all, unbraced length. It is the length of column between two consecutive supports or braces denoted by Lux, Luy in the X or Y direction respectively. So if we have a support here and a support here, so this is unbraced length Lu. But if we have bracing in between like this, so in that case this much will be the Lu, unbraced length. A different value of unsupported length may exist in different direction and must be used to calculate the corresponding slenderness ratio. So first we need to consider the direction. For example, if we have a W section, so if we are going to consider this axis, for example this X axis, so we need to consider the length corresponding to this. If there exists bracing in this direction at the intermediate point, so then we need to consider the distance from the support up to that bracing. Otherwise we need to consider the whole length. But if the bracing is in this direction, there is no bracing in this direction, then we will consider this unsupported length from the first support up to the last support. So we need to consider the corresponding direction to calculate or to select the unsupported length value. So to calculate the unsupported length of a column in a particular direction, only the corresponding supports and braces are to be considered, neglecting bracing, preventing buckling in other directions. So as I have told earlier, that if we are considering this axis, x-axis, but the bracing is also present in this direction at some intermediate point, so then we will not consider this bracing, because if we are considering this axis and we are going to calculate the slenderness ratio about this axis, then we need to consider the bracing about this axis or in the direction perpendicular to that axis, because this bracing in the perpendicular direction will divide the unsupported length. So then we need to consider the unsupported length from support up to that bracing. Okay, next is effective length of a column. So the length of the column corresponding to 1/2 sine wave or buccal shape, 1/2 sine wave of the buccal shape, or the length between the two consecutive inflection point or supports after buckling is called effective length. So for example, we have a pin support over here and a pin support over here, and this is our column, and it will buckle in this direction from this support up to this support. So here we have a single half sine wave. So this is a complete half sine wave. So this portion is half sine wave. So in that case, we have single half sine wave. So this much length will be effective length, LE. But if we have fixed ports at top and bottom, so in that case, our failure mode will be like this. So here we have this much half sine wave. So the distance between the inflection point. So this is 1 half sine wave, and this one will be 1 by 2 of half sine wave. So this half sine wave is actually the effective length. So the length of column corresponding to 1 half sine wave of the buccal shape, or the length between the two consecutive inflection point. So here we have one inflection point and the second inflection point. So this is LE. So the next factor is effective length factor. So to calculate the effective length, we need effective length factor from the unsupported length. When we want to calculate the effective length from the unsupported length, then we multiply it with the effective length factor. So actually this effective length factor is the ratio of length of 1 half sine wave of deflected shape after buckling to the full unsupported length of the column. So this unsupported length factor, or this effective length factor, LE is equal to LE over LU, effective length divided by unsupported length. Or we can write that LE is equal to K times LU. This effective length is equal to effective length factor multiplied by the unsupported length. So this depends on the end condition. So this K value depends on the end conditions and the fact that whether side sway is permitted or not. Whether the side sway is permitted in the column or in the building or in the frame or not. So what is side sway? I have uploaded a video related to the side sway. So you can see that video, that whether the side sway will exist in the building or not, and what is side sway, how it is prevented. So you can follow that video, or you can watch that video to understand what is side sway. Greater the K value, greater is the effective length and slenderness ratio, and hence smaller is the buckling load. So this point need to be understood. So when the K value is greater, so the effective length will be larger. So when effective length is larger, then the ratio KL over R, that will be larger. So for larger slenderness ratio, the load or the buckling load will be smaller. So the column or the section will buckle at the smaller loads. The next is how we can calculate this effective length factor K. So we have a simple expression, K is equal to 1 over N, and N is number of half sine waves. So K value in case of no side sway is between 0.5 and 1, but when there is a appreciable side sway, its value can be equal to 1 or greater than 1. So this need to be understood that when there is no side sway, its value will be from 0.5 to 1, but if there is side sway, its value will be from 1 or greater than 1. So for example, if we first see this condition, this D condition, so we have different types of sports. This is a fixed sport, this is pin sport, and this is sport in which rotation is fixed but translation is free, mean it can sway. And the last one is rotation as well as translation, both are free. So here if we see this D case, so here we have pin sport at the top and pin sport at the bottom. So when this column will buckle, so there will form only a single half sine wave. So we will have N is equal to 1. So K will be equal to 1 over 1 is equal to 1. So our K value will be equal to 1 in that case when we have pin sport at the end. But if we have fixed sport at the end, so in that case we have 1 half sine wave, this is 1 half sine wave, and we have quarter half sine wave here and quarter half sine wave here, or sorry, half of half sine wave. So we have 1 by 2 plus 1 plus 1 by 2 half sine wave, mean N is equal to 2. So when N is equal to 2, K is equal to 1 over 2, 0.5. So K will be 0.5, we can see over here. Similarly, if we see the second case, and at top we have a pin sport and at the bottom we have a fixed sport. So we have a sine wave starting from here up to this point. So 1 half sine wave this one, and this will be 1 by 2 of sine wave, half sine wave. So n is equal to 1 plus 1 by 2. So it is 1.5. So k will be equal to 1 over 1.5. So when we divide, so it will become 1 divided by 1.5, 0.667, or we can say it is equal to 0.7. Similarly, in this case, we have a support at the top in which the rotation is fixed but translation is free, and at the bottom we have a fixed support. So in that case, we have this quarter half sine wave, and then again half of half sine wave, and then half sine wave. So this is 1 by 2 of half sine wave, and this is also 1 by 2 of half sine wave. So n is equal to 1 by 2 plus 1 by 2 is equal to 1. So k will be equal to 1 over 1 is equal to 1. So we can see here the k value is 1. So if we see the next case, E case, so we have a fixed support at the bottom, but the top is free. So here in this case we have only 1 by 2 of half sine wave. So n is equal to 1 by 2. So k will be equal to 1 over 1 by 2 or equal to 2. So here we can see the k value is 2. And in the last case we have pin support at the bottom, and we have a support at the top which is in which the rotation is fixed but translation is free. So the curvature will be like this. So this is again a half of half sine wave. So n is equal to 1 by 2. So k will be equal to 2. So we can see over here k value is 2. So this is the way how we can calculate this effective length factor k when we have defined end conditions. Mean either it is fully pinned or fully fixed. But in the case when the supports are not predefined, mean it is partially fixed, partially restrained, so in that case the scenario will be different. So if we have partially restrained columns, mean at the end the columns are partially restrained. In case of frame structure, we have columns like this. Here we have beams and then beams. So in that case, this point cannot be fully fixed. So there will be partial fixity at this position. So in that case, we need to calculate, or we need to use these charts to calculate the k value. So this is the first chart is for the frames in which sway is prohibited or sway is restrained. So in that case we can use this chart, and in case of frames where side sway is permitted, so in that case we will use this chart. So to find the value of k from this chart, we need to calculate GA and GB. GA will be at this joint and GB will be at the bottom joint. And then we need to align these values. This is the alignment chart. So for example, we have a GA value 2 and GB value 0.4. So we will join these 2 points with the help of a straight line, and the point at which this line intersect this intermediate scale which is corresponding to k, so that will give us the k value. So here we see its value will be 0.75. So k will be 0.75 in this case. So in the similar manner we can calculate the value for this chart. So the point where this line intersect the k bar or k scale, so the corresponding value can be considered as a k value. So the question is how we can calculate this GA and GB. So GA or GB is actually the ratio of flexural stiffness of columns and flexural stiffness of beam joining at the joint. So for example, if we see this joint A, so here at this point we have 2 beams and 2 columns meeting at that joint A. So we need to calculate the flexural stiffness of these 2 columns, the upper one and the lower one, and we also need to find the flexural stiffness of this beam as well as this beam, and then we need to take the ratio. Mean, for example, this column is C1, C2, this is B1 and this is B2. So G will be equal to flexural stiffness of C1 plus flexural stiffness of C2 divided by flexural stiffness of B1 plus flexural stiffness of B2. And this flexural stiffness is simply equal to EI over L. So we need to find the EI over L value for all these beams and columns meeting at that point. So we can calculate this G value at point A and at point B. Once we have these G values, then we can easily calculate the K value, or we can easily find the K value from those alignment charts. Okay, so K value for truss or brace frame members. So in case of truss members, the K value can be considered equal to 1, because in case of trusses, we assume that our connections are pinned connections. So we consider the pin connection at the end of the member. So in that case, we will have a curvature like this. So N will be equal to 1 and K will also be equal to 1. And in case of braced frame, we can also consider its value equal to 1. So here we have models that when we can consider the K value 1 or more than 1, or how we idealize the frame. So if we see the first case, we have all the pin supports, but at this point this is braced. It means there is no side sway. Side sway is restrained in this frame, but we have pin support at the top. So here if we see this column, so this column at the top we have pin support and at the bottom we have pin support. So there will be single curvature. We will have N is equal to 1. So the K value will be equal to 1. And if we see this second case, so here we have fixed support at the bottom, pin support at the joints between the frame elements, but the frame is restrained against the side sway. So we have pin support at the top and fixed support at the bottom. So we can idealize this case, and in that case the K value will be equal to 0.85. But if we have fixed support at the bottom, our frame is high and the top connections are pinned, but there is no bracing. So in that case we can idealize it in this way. So there will be sway in the outward direction. So here we have 1 by 2 of half sine waves. So K will be equal to 1 over 1 by 2 equal to 2. Similarly, if we have a frame in which the beam is rigid. So when the beam is rigid and the side sway is also prevented by using bracing, so in that case we will have fixed support at the top as well as fixed support at the bottom. So in that case the scenario will be this one. We will have 0.7 value of K. If we have a frame like this, that the beam is rigid and the side sway is not permitted, so in that case there will be no rotation but translation will be allowed. So at the bottom we have fixed support, so translation as well as rotation is prohibited. So we have 2 half sine waves, so half of half sine wave. So this is 1 by 2 half sine wave, and this will be 1 by 2 half sine wave. So N will be equal to 1 by 2 plus 1 by 2. So it is equal to 1, and K will also be equal to 1. So in this way we can idealize these frames and we can calculate the K value. So next is correction in slenderness ratio for single angle section. The single angle compression members may undergo torsional buckling. So at lower load than the load at which buckling may occur about x, y or z axis due to eccentricity of loads. So in case of single angle section, there are chances of torsional buckling. So the torsional buckling will happen at the lower load as compared to the load corresponding to the buckling or the lateral buckling of the member. So in that case we need to correct our slenderness ratio. We need to increase the slenderness ratio to consider the effect of torsional buckling. So hence, in order to closely estimate the capacity of equal leg angle or unequal leg angle connected through the longer leg, the slenderness ratio is need to be modified. So we can modify the slenderness ratio. So for that we need to first investigate what is the L over Rx. For example, we have a member angle section connected like this. So this leg is connected. So we need to calculate this Rx value. So if this leg is connected, so we will consider the R value corresponding to this parallel axis. And then we take the overall length divided by this R, whatsoever this Rx or Ry, for example. This length is connected, so then we will consider this axis to calculate the R value. So it will be Ry. So whether it is Rx or Ry, we can say it is Rx. So we need to calculate this value and then we compare this with this expression. It should be more than 0 and less than 80. If it is more than 0 and less than 80, then we can calculate the corrected value of slenderness ratio by using this expression 72 plus 0.75 L over Rx. So Rx is the radius of gyration about the axis parallel to the connected leg. So again I can show it. If this leg is connected, so we will consider this axis to calculate the R value, so it is Rx. And if this leg is connected, so we need to consider this axis and it will be Ry. So similarly, if this L over Rx is greater than 80, so we can calculate the modified slenderness ratio by using this expression 32 plus 1.25 L over Rx, and it should be less than 200. And similarly, if we have a space stress, then we can follow these expressions to calculate the corrected slenderness ratio for single angle sections. So next is the built-up section, and we need to calculate the modified slenderness ratio for built-up section. So shear connector are stay plates between the elements of a built-up member. So when we make a built-up section, so we need to provide shear connectors or stay plate between the built-up section. For example, we have this built-up section made of this 2C section, so we need to provide these stay plates, lacing or shear connectors. So the built-up compression member composed of two or more hot-rolled shapes shall be connected to one another at an interval by stay plates or shear connectors such that the maximum slenderness ratio A over Ri of individual element between the fasteners does not exceed the governing slenderness ratio of the built-up member, that is greater value of KL over Rx or KL over Ry. So what it means? For example, we have a box section made up of angles. So we need to use these lacing elements as well as tie plates to connect the section at different locations. So if we see in the plane, so we will, or in the elevation, it will look like this. So this overall section will have slenderness ratio Rx as well as Ry, mean KL over Rx and KL over R about Y axis. So the larger value out of these two will be the governing value. Similarly, if we see these individual sections, for example this one, so if we have tie plate, one tie plate over here and the second tie plate over here, so between these two tie plates, this much length of the individual member, so it can also buckle. So it will have a certain length L, and the radius of gyration of this individual member mean Rx, Ry or Rz. So the smaller value out of these three. So L over Ri mean R minimum. So this will give us the slenderness ratio of this individual member. So the slenderness ratio of this individual member should be less than the governing value out of these two slenderness ratio. So we need to design these tie plates or lacing elements in such a way, or these shear connectors in such a way, that the slenderness ratio of this individual member should be less than the governing slenderness ratio of the overall section. So this is because if the slenderness ratio of this individual member is greater than the overall slenderness ratio of the member, so the portion or this portion of the member will buckle before the overall buckling of the member. So we need to ensure that the overall section buckle, but the local or the part of the section should not buckle. So shear connectors are also required to transfer shear between the elements of built-up members that is produced due to the buckling of the member. So actually, when the two members, we have two members like this, and these are bent in this manner, so the shear stresses will develop between these two members. So as we have seen in the very first chapter about the concept of shear, so when we have two plates and we try to bend those plates, so they will slide against each other. But if we provide shear connectors or shear bolts, so in that case these shear bolts will resist the shear between these two plates, and the bending or the bending strength will be enhanced. The stiffness against the bending will be enhanced. So to resist the shear between these two elements of the built-up section, we need to provide shear connector so that the shear can be transferred from one member to the other, as well as their stiffness could be increased. And when these are connected with the help of these shear connectors, so the section will behave like a single unit. So here we can see, so these are the shear connectors. We can say these are the lacing and these are battens or tie plates. And the slenderness ratio of this individual part should be less than the overall slenderness ratio of this section, of this built up section. So following notations are used for the further discussion of the effect of spacing of shear connectors. So actually we need to consider the modified slenderness ratio when we use this lacing element as well as this tie plates. So here A is the distance between connectors. So the distance between connectors, the clear distance between the connector is equal to A. R is minimum radius of gyration of the individual components. So if we see this C section, so the radius of gyration of this section, the minimum radius of gyration. So A over Ri is equal to the largest column slenderness ratio of individual component. So this individual component, this portion, so A over Ri is the largest slenderness ratio of that component, corresponding to x-axis, y-axis, z-axis, or whatsoever is the weak axis. KL over R naught is the column slenderness ratio of built-up section. So the slenderness ratio of built-up sections. For example, we have built-up section like this. So the slenderness ratio of this built-up section will be KL over R naught. And KL over RM is the modified column slenderness ratio of built-up member. So we need to modify the slenderness ratio in case of built-up section when we have these shear connectors. So if buckling mode of a built-up compression member involves relative deformation that produces shear force in the connectors between the individual parts, the modified slenderness ratio is calculated as follows. So for snug tight connections, we can calculate the modified slenderness ratio by using this expression KL over R square and A over R square. And for welded connection or fully tightened connections, so we need to see if A over Ri is less than 40, so the modified slenderness ratio will be equal to the actual slenderness ratio of the built-up section. But if A over Ri is greater than 40, in that case we need to calculate the modified slenderness ratio by KL over R square plus KIA over R square. So here KI is 0.5 for angle back to back like this, 0.75 for channels back to back if the channels are like this, and 0.86 for all other cases. So by using this expression we can calculate the modified slenderness ratio. But here one thing which need to be noted, that we only calculate the modified slenderness ratio when we have relative deformation between the parts of built-up section. So we can visualize this thing over here. So KL over R modified should only be used if buckling occurs about such an axis such that the individual member elongate by different amounts. So for example, if we see this angle section which is back to back, so here if we consider this x-axis and the bending about this x-axis, so in that case whatsoever will be the deformation in this channel section, the same will be over here. So this, for example, this portion is in compression and this portion is in tension. So both the members have similar value of deformations. So in that case we need not to consider the modified slenderness ratio. But if it bends about this y-axis, so here one member will be in compression and the other member will be in tension. So in that case there will be relative deformation between these two components. So for that we need to consider the modified slenderness ratio. So in that case we need to consider the modified slenderness ratio when there is deformation, relative deformation between these two elements of the built-up section. So one will be in compression and the other one will be in tension. So the slenderness ratio of individual component between the connectors Ka over Ri should not exceed 75% of the governing slenderness ratio of the built-up section. So the slenderness ratio of individual member A over Ri should be less than 0.75 of R maximum.